Uh, Good afternoon, everyone. Myself, Dr. Manoj Kumar Singho, as Assistant Professor in the ECE Department. I welcome all of you to the first webinar on the ECE Departmental Distinguished Lectures. It will be delivered by Professor Achyantha Venugopal. He is the Director of CSR NPL and Professor TIFL. To inaugurate this event, I request our Pro-VC, Professor D. Narayana Rao, to start the event. Sir, inaugurate this event, sir.
Okay. Thank you, Dr. Manoj. The distinguished speaker, Director of the prestigious and premier CSIR National Physical Laboratory, New Delhi, and extremely accomplished scientist of international repute, Professor Venugopal Achyantha, Head of the Department of ECE, Dr. Ramesh Vaddi, Dr. Manoj Kumar Singha, faculty members, research scholars, and students. I extend a warm welcome to all of you to the distinguished lecture being organized by the Department of ECE. You are kindly aware that during the last few years, there is a great interest to carry out research on metamaterials. Metamaterials have the exotic properties which the naturally existing materials do not have. Rather, metamaterials are engineered materials that possess the properties which the naturally existing materials do not possess. This I am explaining particularly for the benefit of the students. Metamaterials exhibit negative permittivity and or negative permeability. Metamaterials extract their properties or possess their properties from their structure rather than the composition of the material. Metamaterials, you are aware, exhibit negative refractive index and hence find potential applications in stealth aircrafts, etc., in which Professor Venugopal is also working on stealth. Potential applications of metamaterials are diverse and include optical filters, medical devices, remote aerospace applications, sensor detection and infrastructure monitoring, smart solar power management, crowd control, radomes, high-frequency battlefield communication, and lenses for high-gain antennas, improving ultrasonic sensors, and even shielding structures from earthquakes. Metamaterials offer the potential to create super lenses. Metamaterial research, as you know, is interdisciplinary and involves fields such as electrical engineering, electromagnetics, classical optics, solid-state physics, microwave and antenna engineering, optoelectronics, material sciences, nanoscience, semiconductor engineering, and others. I just mentioned a few areas and a few interdisciplinary subject, but it has great potential. Thus, metamaterials is a new field of research and an exciting area of research. I congratulate our colleagues, Dr. Ramesh and Dr. Manoj Kumar Singha, in inviting such a great scientist, Dr. Venugopal, to deliver the lecture on metamaterials. For the benefit of the members present here, I wish to inform you that SRM University, Andhra Pradesh is established in July 2017 as a multi-stream research intensive university. Presently, we are offering BTech and MTech programs in different disciplines, and we have about 5,600 students from different parts of the country, and a few students are foreign nationals. 181 students, including a few net qualified and a DST Inspire Fellow, have enrolled for PhD programs in different disciplines. We have appointed 213 faculty members having PhD degrees from premier institutes such as IITs, IISc, and reputed universities. 4 DST Inspire faculty, 1 DBT Ramanujan Fellow, 1 Srinivasa Ramanujan Fellow are working with us. In the year 2018, we have started School of Liberal Arts and Social Sciences, and also School of Entrepreneurship and Management to provide holistic education as envisaged by National Education Policy 2020. Our faculty members are quite active in research. This university is a nascent university, about 4-year-old, and research activities we have started only 2 years back. And in these 2 years, our faculty members have published more than 700 papers in highly reputed journals, including nature communications, nature microbiology, proceedings of the National Academy of Spain, PNAS, IEEE transactions, and other reputed journals. Some of our faculty members have published 20 papers in Nature Index journals. Our colleagues, Dr. Karthik Rajendran, Dr. Imran Pancha, and Dr. Lakvir Singh, are recognized among the top 2% scientists of the world as compiled by Stanford University. Many of our faculty members have received sponsored research projects from DST, DBT, National Supercomputing Mission, DRDO, BRNS, UGC, DAE, NABARD, and a few industries. One faculty member, Dr. Sudarshan Govindarajan, received the prestigious DBT Welcome Trust Award. We have established SRM Amar Raja Center for Energy Storage Devices jointly with Amar Raja Batteries Limited, the leading battery manufacturer in the country. We have established Center for Weather Forecast in association with India Middle Department IMD. This center located in the campus provides weather forecast for the entire state of Andhra Pradesh. We have taken up a few special projects, development of gold foam for jewelry applications in collaboration with Tanishq Jewelers of Titan Industries and Hari Vaman Pete of Maharashtra. 3D printing of gold jewelry, once again in association with Tanishq Jewelers. We have initiated 3D printing of bioimplants in association with Concordia University, Canada, and All India Institute of Medical Sciences, AIIMS, Mangalagiri. Metal additive manufacturing for strategic applications for DRDO and ISRO in collaboration with IIT Hyderabad, IIT Jodhpur, and ARCA Hyderabad. Also, we have initiated development of hydrogen-powered fuel cell-based train in association with the Integral Coach Factory of the Ministry of Railways. We will demonstrate the fuel-based train in the next 3 years. At SRM University, we provide the students research-based learning for knowledge creation and innovative ideas. Further, we train the students with a desire to learn and with a desire to do and enable them to take up challenging tasks that they encounter in their careers. We prepare the students to participate in world affairs by providing them with learning experiences that across countries and cultures. We do recognize that the students' knowledge base must be sufficiently flexible to cope up with the 21st century job scenario. We do well realize that universities are viewed as creators of new knowledge, innovative ideas, providers of talented and skilled manpower, agents for social changes, symbols of international attention and prestige. With these motives, SRM University Andhra Pradesh is established as a new age research intensive university. Jai Hind, Jai Bharat, and Jai Vigyan. Thank you one and all.
Thank you, sir. Dr. Manoj, please. Okay. Thank you, Professor D. Narayana Rao, for his talk, for inaugurating this event. So today's speaker is Professor Venugopal Achanto. Today he is going to talk. The title of the talk is Metamaterials and Their Applications. Abstract of the talk is that metamaterials are designed materials with unique properties that may not exist in the naturally available materials. These are designed with sub-wavelength size components. In this talk, he will briefly introduce the metamaterials, and then he will discuss few metal dielectric and all dielectric metamaterials and their applications in wide-ranging areas, covering still single photon emitters, reusable biosensor, and among others. His brief biography is that he obtained his PhD from TIFI, Mumbai, and PhD in electronics from Tokyo University, Tokyo, Japan. He is presently director at CSI National Physical Laboratory, Delhi. Till now, he has published more than 140 journal publications. Sir, I don't want to spend more time, sir. I request Professor Achanto Venugopal to start the talk.
Thank you. Thank you very much, Dr. Singha, and thank you, Professor Narendra, for initiating really academic interactions, and it's really impressive to hear about the facilities you're creating and the research you're carrying it out at SRM. So I'm thankful to Dr. Gautam and Dr. Ramesh also for giving me this opportunity. Right. So I'll be presenting about metamaterials. Professor Narendra already given a very crisp introduction to metamaterials, which makes my job easier. As a teacher, we are expected to repeat the concept a couple of times so that it just gets embedded in the student's mind. So I'll be repeating what Professor Narendra has briefly explained. Right. So when light or any electron falls on a material, how does that material respond to this electromagnetic radiation? It can be just a pure electric field, it can be an applied magnetic field, or it can be like a radiation, right? Optical, visible, near infrared, or terahertz, right? So any of these radiation when falls on a material, so the material responds to the electric and magnetic fields depending on its properties. For example, the medium has the epsilon dielectric constant and mu the magnetic permeability. Right. So the electric field of the incident radiation gets response from the epsilon, the dielectric constant of the material, and the magnetic permeability of the medium will respond to the magnetic field of the incident radiation. Right. So epsilon and mu, I probably will close this. Right. We have epsilon and mu for the materials which are defined. And as I said, epsilon is a response to the electric field and mu to the magnetic field of the incident radiation. Right. So depending on epsilon and mu, they can be positive or negative. Right. So we'll see what are the consequences, right, of these signs of each of these. For example, if we have epsilon negative and mu is positive, the box which is shown here, so that forms the second quadrant of this full circle which you're going to draw. So which is mu versus epsilon. So when you're plotting it, the second quadrant will show epsilon is negative, but mu is positive. If you take metals have large free electrons, large number of free electrons. For example, plasma, right? So all these have epsilon less than 0 and mu positive. Right? If you go to first quadrant, here both epsilon and mu are positive. Most of the materials which we see, the so-called insulators or the so-called dielectric materials, they all have epsilon and mu, both are positive. Right? The refractive index of the material, which we study in optics, is basically given by square root of epsilon times mu. Right? Typically, we take non-magnetic material, so mu is taken as 1. So when we write n is equal to square root of epsilon, it's for non-magnetic materials. So most of the materials which we see in nature are both epsilon and mu are positive. And whatever we study about Doppler effect, for example, when the source of frequency is approaching us, we perceive the frequency to be increased, right? So all these things are in these positive index materials or naturally existing materials, right? So in the fourth quadrant, we'll see epsilon and mu. Epsilon is positive, mu is negative. So some form of magnetic material. So for example, ferrites show this kind of response in certain frequency ranges. But the most interesting thing of late is demonstrated in this third quadrant, where both epsilon and mu are positive. So because of which the refractive index is now negative, right? Unlike naturally existing materials, as Professor Narendra mentioned, now these are negative refractive index materials. Right? Why is this interesting? Because all what we study in the textbook will become bizarre, because now the source, when it is approaching us in a negative index medium, so the frequency will be reduced compared to in a normal medium where the frequency is perceived to increase. So the properties are really different from what we see in naturally existing materials. These materials do not exist. The negative index materials do not exist in nature. And so we have to design these structures, right? So that's why these are called metamaterials, because they do not exist in nature, right? So what are some examples? So for example, these are images from literature. So where you have a rod and these so-called split ring resonators. So there is a ring. Instead of a ring, you just open up, so they're not connected. So it works like a capacitor. And then you have inductance and resistance coming from the metal film, which is here, right? So you basically are designing a LCR circuit. By designing the parameters of this, you are making it resonant for some particular frequency, right? At that particular frequency, we are expected to have negative epsilon and negative mu, so negative refractive index. So what are the consequences? As I said, one is the Doppler effect. So other is if you put a rod inside a glass, so you don't see much of distortion in the rod. But if it is put in a liquid with refractive index more than 1 is used to fill the glass, you see there is a bending of the light. The refraction happens, and which leads to as if the rod is now kind of broken, right? So, but if you have a negative index material, if the liquid is negative index, so what you see is instead of split this way, now we are seeing it in a completely opposite direction, right? So this is a kind of a distortion which you will expected to see if you have a negative index liquid, right? So just to say, metamaterials are artificially designed structures. One simplest feature, unique feature of this is if you're building a lattice, if you're building some structure, we take some unit cell, right? So in case of a metamaterial, the unit cell dimensions are much smaller than the incident light wavelength or whatever radiation we want to use. So the unit cell dimensions are much smaller than the wavelength of light. Properties are generally approximated by an effective electromagnetic parameters epsilon and mu, effective dielectric constant and effective magnetic permeability, right? So naturally existing materials, we generally talk in terms of chemical composition and band structure, right? But in metamaterials, we talk about the shape, size, geometry, unit cell. You take one shape and then you repeat it, or you repeat it in certain fashion, right? So how this arrangement of these unit cells is going to control the properties of the metamaterial. So there are several unique phenomena that do not exist in nature, but we can easily tailor them in by modifying these geometrical parameters of the metamaterial. Right? So some interesting things are these are way back in 4th century AD. People had this wine cup, and of course it's a very special cup for an emperor. It's a Roman cup. So the properties of this is like if you put a candle inside, right? The light transmitted makes it look like red in color, like the one shown in the on the right side. But if you shine light from outside, the cup looks green in color. So the reflected and transmitted colors are different. So the glass with which this cup is made is the ruby glass, which has gold nanoparticles in it, right? There are biosensors which are available from 1990s. So another interesting thing is the world's tiniest laser, right, emitting at 531 nanometers. So this was reported in a structure like this. So you have a gold nanoparticle at the center, and you have this sodium silicate shell filled with a dope, a dye, right? So when you shine light, so the dye is going to absorb the light and then going to emit its own color light. So that light is going to get absorbed by the gold nanoparticle, which enhances the field nearby and leads to lasing action eventually. So there is a diffraction limit in optics, right? So which says that, for example, we cannot use an optical microscope to see an atom. The reason is the wavelength of light is much, much larger than the particle size. So when the light is passing through an atom or a particle which is much smaller than, say, lambda by 2, where lambda is the wavelength of the incident light. So there is very little distortion in the wavefront. How do we see an object, or how do you know that like we have something in front of us. It's because the reflected light is coming to us, or if there is some scattered component which is coming to us and makes the wavefront distorted, so that either it's a dark or slightly, there's a contrast which comes in, either little more darker or little more brighter, which makes us visualize that there may be some obstacle in the path of the light. But if that particle is too small, we'll not be able to see that, right? Or perceive that there is something in the path of the light, right? So this is called the basically the diffraction limit, right? So for using this optical wavelength, so the lens size, for example, has to be at least λ/2, or of the order of like wavelength of light, right? So if you take blue light, so you need the size of your particle to be at least 400 nanometer, or the lens has to be at least 400 nanometers. But here, as shown here, like on the top right, so people have shown that you take these tiny discs, metal discs, these are silver nanoparticles, and that can be, this array can be used. You shine light from the left-hand side, and then this array is going to focus light to much smaller than wavelength of light. So for example, the strip which is shown here has a width of about 250 nanometer. So then there is some surface enhanced Raman spectroscopy based for cancer cell detection. Then you have highly directional lasers, right? So these are all shown, right? So the basic concept, the basic physics, or the basic idea behind these things is like, if you have a metal nanoparticle, you have large number of free electrons on the metal surface, right? When your incident light frequency, right, matches with the resonant oscillation of the frequency of these electrons, which can move on the surface of the metal, right? So then energy can transfer from incident light onto the nanoparticle, right? So that's what that particular frequency of this electron oscillation depends on the what metal material you have taken, what is the size, what is the shape, right? And what is the surrounding medium. So once these are fixed, so then the resonant frequency of oscillation of these electrons is fixed, right? Now, when you shine light on top of this nanoparticle, so that there is absorption of this particle into this resonant oscillation of electrons, and you'll have that particular frequencies are dropped because they're absorbed into the particle plasma. So you'll get some scattering colors from these nanoparticles. This you can see, for example, in windows, colorful windows of old buildings, right? So these are metal nanoparticles, but these are coated with the different salts in what is used in generally. But the idea here is because this radiation is localized to the surface of these metal nanoparticles, these are called particle plasmons. Similarly, you can have a metal and a dielectric, a metal and an insulating layers. So the metal has large number of free electrons, right? So these free electrons can be excited under certain conditions, that you have more number of electrons at one place, less number of electrons at one place. So like that, okay? So it's like a charge density wave. So when the incident electron kicks this incident photon, for example, incident light, kicks these electrons, it transfers some momentum, so the electron starts moving. So, but under certain conditions, you can have a positive, negative, positive, negative, net positive, net negative, less number of electrons at one place, more number of electrons at another place. So this can propagate, this wave can propagate along the metal dielectric, metal insulator interface. And one of the properties, interesting properties of this is, so the field which is localized at the interface will exponentially decay when we are going away from the interface. Okay? So that's what is shown as this exponential decay of the field on either side, into the metal in the bottom and into the dielectric on the top. And metals have a skin depth, so because of which the field cannot propagate. So the field decays much faster in much shorter lengths compared to in a dielectric. Right? So depending on the metal and dielectric epsilons, right? So you can, the dispersion relation is given by this, right? So the dispersion relation basically tells us the energy and momentum conservation. For a given energy conservation, so the if you're shining a light, so the photon energy should match with the energy of the electron, right? And similarly, the photon momentum also has to match with with this charge density wave, which we call the surface plasmons, the momentum of the surface plasmons, right? When we're talking about band structure, we again plot E versus momentum. So that again says what are the energy levels, what are the allowed transitions where energy and momentum conservation both are satisfied. So if they're not satisfied, we'll start seeing those band gaps and forbidden bands and all this, right? So similarly here for similar to the electrons, so here we can talk about plasmonic band gaps and other things, right? Okay. So we have been working on these metamaterials for almost like 15 year plus. So we have large number of results. I'll be talking about a few of these, right? So the metamaterials can be used, for example, for single photon emission, which I'll show you, for a biosensor, and these are called as all dielectric metamaterials. So far I only talked about metal and the metal dielectric interface, right? So the metal also absorbs light. So metals are lossy. So that's where like people started thinking about, are there alternatives to metals? So then they came up with, instead of using metals, now let us start designing these metamaterials with, for example, only insulating materials, only dielectric materials, right? So these are known as all dielectric metamaterials, right? So the initial metamaterials began with the definition that they are negative index materials. Then the plasmonic metamaterials came where epsilon can be negative and mu can be positive, but we can design the properties by choosing the unit cell dimensions to be smaller than the wavelength of light, and we can design at will the properties which we want, right? Now it's become even broader, not just metal and dielectric metamaterials. You can also have purely dielectric materials. These are called all dielectric metamaterials. So I'll show some examples of this, right? First, I'll talk about the perfect absorber, right? So when you have a material, the losses are broadly into scattering or reflection or absorption, right? So how do we overcome these and make sure that, for example, if we have a solar cell, right? In a solar cell, we have p-type, n-type, right, material, so that you have a junction forming between them, so the p-n junction. Now, all the light which is falling, we want that light to be absorbed in that thin p-n junction region, so that maximum number of electrons are generated, right? So that you can extract them out and you have these either the voltage or current, whichever you're looking for, right? That just one possible application. If you want to use a photodetector, for example, the efficiency depends on how many electrons are, how much of the incident light is absorbed, and how many electrons are generated out of it, right? So that's what I'm showing here. So it's basically, if you have, I mean, in electrical engineering and even in electronics, we study about impedance matching. The same thing also holds for optics, right? If your refractive index is same between two different materials, right? So then your reflection will be suppressed. So the impedance of a medium is generally given by square root of mu by epsilon. So mu is magnetic permeability and epsilon is a dielectric constant. So the reflectance from a surface, from an interface, is given by Z1 minus Z0 by Z1 plus Z0. Right? So again, Z1 and Z0 are for the material from which the reflection is happening, and top we are from the medium from which it is falling, we consider it to be Z0. For example, air. Right? So when we have Z1 equal to Z0, so that is at the interface, the impedance is matched. So you have resistance is 0, so you have 0 reflection. Okay. So, and absorption is 1 minus R. So you'll have ignoring the transmission, because if you take a metal, for example, a very thick metal, a ground plane kind of thing, so then your reflection is suppressed, and your thick metal is going to block the transmission. So you're going to get 100% absorption. So that's the concept of perfect absorber when it was designed, right? So there are, I mean, the first proposal and demonstration was in 2008. This was at say 11.2 gigahertz frequency. So this is, they made a pattern like this. So there is this metal strip which is shown by this, and on top of it they have this structure which is shown here. So by designing the structure, they showed that one can get very close to 100% absorption in these structures. Right. So later people used just simple grating structures of silver, for example, silver and silicon dioxide, and silver thick layer of silver underneath. Okay. So then cross gratings was used to make it a broadband perfect absorber. So the idea here is, if you take a very thin layer of dielectric in the center and metal on the top and the bottom, so the current in the top metal goes, say, left to right, and the bottom it goes right to left. So these two cancel each other. So the field is maximum, right? And is maximized in the very thin dielectric layer with even a weak absorption is okay. And with that, we can get 100% absorption in these structures. So we showed that we can actually have design these structures for broadband applications. So by taking different shapes, right, and for covering different wavelength regions, so we can design the broadband structure and showed that we can go up to 99.8% absorption in a very thin silicon layer, for example, of 10 nanometer or smaller, right? So this is one example where this is a vanadium dioxide layer, which has a phase transition from a metal to dielectric, right? So we need a dielectric layer here to see the perfect absorption. ITO and the gold are metallic in nature, right? So this has to be dielectric. So when you increase the temperature, initially room temperature, it's a dielectric, but when you increase the temperature, the VO2 goes from dielectric to metal. So then that also starts reflecting, right? And is that correct? Like, so, sorry, it goes metal to dielectric transition, right? So that's what is shown here. So as you increase the temperature, so suddenly this patch is invisible, right? So what it means is, like, your infrared wavelengths are coming, and when you change the temperature of your vanadium dioxide, so it changes its phase from metal to dielectric or dielectric to metal, from which direction of the temperature we come from. At higher temperature, it acts as a dielectric where a perfect absorber is possible, right? So all the incident radiation is absorbed within this VO2 layer, vanadium dioxide layer. And so if you're using an infrared camera, which is generally used for night vision goggles and other things. So for example, this can be used for making a fabric where with the pixels are there. So each pixel is for example, of this shape and sizes are given here. So by covering an armored vehicle, for example, a truck, which is carrying, say, soldiers in the night, so you can cover these and switch these pixels to mask. So whatever infrared radiation coming out or reflected or emitted from the bodies and other things, they can be suppressed by choosing the pixels which are going to absorb. So a long truck can be made to look like a small car, right? So this can have stealth applications using this perfect absorber metamaterial. Okay. So as I mentioned in one of the early slides, the first commercial biosensor came in 1990, right? So here, just by launching either a white light at a critical angle, or have one single wavelength and vary the launch angle. So you can decide, like, so the with and without the analyte on the surface here, you measure the reflection spectra, and the shift in the spectrum with and without analyte is going to tell you what is the change in the refractive index and the presence of the analyte and what concentration of analyte is present there. So this was the simplest biosensor, which is commercially available for about 30 plus years now. Right? If you want to enhance the sensitivity, so one way is to use this so-called ellipsometric measurements. In ellipsometry, what we do is instead of shining light of, any arbitrary polarization or unpolarized light, here we take very specific polarizations, S and P polarized light, and then look at their reflection properties, right? And the two parameters which are very important are basically, if you take the reflection coefficient for S and P polarizations to be RS and RP, right? So you take this ellipsometric parameter psi and delta. So psi is, or tan psi is ratio of P to R reflection, P to S polarization reflection coefficient ratio, and delta is a change in the phase for S to P polarized light, right? So if you measure the differential phase, that is with and without analyte, if you measure the change in the delta, that can be used as a very high sensitive biomolecule detection. So there was a proposal that you can actually go down to a single biomolecule detection, right? That much of sensitivity is possible. This was shown in 2013, and a picomolar detection has been demonstrated also in 2018, right? So we designed a structure which is reusable, right? If you take these structures, so they have metal on the top, so which makes it very restrictive, right? So you cannot really reuse them, right? So we started designing a structure with a dielectric on the top, preferably glass. Silicon dioxide is nothing but glass. So if you make it index matching or impedance matching, so that index is refractive index. If the top SiO2 has same refractive index as, for example, a glass flow cell, right? So then we can put a flow cell on top of it, flow the solution with analyte, and then measure our top reflection measurements as in the normal ellipsometric conditions. So we designed a structure which showed the highest Q factor and the figure of merit, so that our sensitivity is expected to be very high, right? So we compared simulations and experiments. So we have broadband, a very weak dependence on the incident angle, and also it works for a broad wavelength range, right? So we detected for 3 different biomolecules, and the lowest we could detect was few hundred femtomolar. So we're still working on measuring the ultimate limit of these detector or the sensor. So this can also be used as a pure vanilla refractive index sensor. So change in the refractive index. So when water has refractive index 1.5, now you put your biomolecule inside. So the effective refractive index is going to be different from that of water, depending on the concentration of the biomolecules which are inside the water. So now we can choose, we can detect the refractive index of the material, and from that we can estimate what is the concentration of the biomolecule inside the solvent. Right? So I'll switch gears and I'll show you some work which did with Dr. Gautam Rana, who is now at SRM. So this is, can we mimic atoms in metamaterials? So I said metamaterials can be designed for any particular application which we want. So here I'll show some example where atom-like features can be mimicked in metamaterials. These metamaterials are bulky, right? So they're much bigger than atoms. But still, in these materials, we can mimic properties of atoms, right? So one of the properties is for example, if you have 3 energy levels, so we can have a pump beam and a probe beam. So the strong pump beam is going to change the energy levels slightly, right? So because of which the probe beam absorption will get modulated, right? So this is known as electromagnetically induced transparency. So initially we have 3 layers. So the pump, without pump, the probe is being absorbed. with the pump beam. So because of the coupling, so the level is going to slightly shift or split, whatever. So because of which, so the absorption of the probe beam is going to get reduced. So your probe beam transmission is going to increase in presence of a strong electromagnetic field, which is the pump beam. So this is called electromagnetically induced transparency. So we designed a structure which is known as a dolmen structure. It has two legs and a horizontal bar on the top. Okay. So this has been well studied. The dolmen structures are well studied. So if you have a dipole, right, you have a plus and minus at these 2 points. For example, blue is negative and red is positive, right? So you're inducing a quadrupole into your two vertical legs, which are on below this horizontal rod. So the horizontal rod, we are exciting a dipole, negative and positive at the two edges. And this dipole is going to induce, so the negative is going to induce a positive in this vertical rod, and the positive here is going to induce a negative here. So you'll have a quadrupole, which is formed only when the dipole is there, right? So we can control this absorption between these, how much absorption happens or how much transmission happens by introducing another horizontal rod, nano rod under this traditional dolmen structure, right? By controlling the position of this bottom rod, you can induce a counter propagating quadrupole into these two vertical rods, so we can control how much transmission is happening. So we showed that in addition to this broad transmission, which we expect for a single dolmen, like, so we have this enhanced transmission here, which is happening because of this presence of this bottom vertical rod. So this is known as the plasmon induced transparency, and we can control the sorry, this question mark is gamma, which is the line width. We can control the line width or the quality factor of these modes. So we showed very high Q cavities from this. So another example is a stretchable metamaterial. So what we did is these patterns are made on a substrate, and then we deposit a long chain polymer known as MPTMS, the mercapto something, which has a thiol which attaches to the gold very strongly. So once for example, a PDMS, a flexible polymer is film is put on top of this with MPTMS on top, we can actually peel off this pattern onto the PDMS, and when we stretch it, the size and shape of these unit cells are going to modify, because of which we can start seeing these coupled resonant features, because of which, like, so we saw features like what is known as this see, these Otler tone splitting is the word which is used. In simpler terms, it is that you have two modes which are coupling with each other, because of which instead of having these two levels at the same position, you'll start seeing this splitting. So both of them will have orthogonally polarized response. So you start seeing this splitting. Initially at low stretching, you see this enhanced transmission like the EIT, and at higher stretching, you start seeing this splitting of these energy levels into two. Right? So these are atom-like properties. So the metamaterials can be also used for example, quantum communication, and quantum information is very, very popular nowadays. So we can look at, for example, single photon emitters, which are interesting or important for quantum key distribution or quantum communication. Right? So one of the ideas is to use these so-called hyperbolic metamaterials. If you have a slab of material, you have the momentum is defined as kx, ky, and kz in the three directions. Kx, ky can be in plane, and kz can be in the propagation direction of the incident radiation. Right? So once you have it, if it is an isotropic medium, you'll get a spherical momentum, the picture like this, right? But if you have kx and ky are of one sign, signature sign, positive or negative, and the kz is of opposite sign, So then you start seeing hyperbolic dispersion profile, as you're seeing in these two pictures, B and C here. The consequence is that epsilon ZZ can be negative, which means in the vertical direction, the material is going to act like a metal, and in plane, it is going to act like a dielectric as an insulator, right? Or vice versa. It can be metallic here and dielectric in the vertical direction, right? So once you have these, you can actually get a really directional emission from these structures. So we have showed this by having an antenna, a patch antenna on the top, and a single nanoparticle, a single quantum dot is put inside this central layer. So you get like very directional emission, because when you're talking about single photons, the room light has, say, 10 power 15 of the order of 10 power 15 photons which are coming, right? We are talking about collecting a single photon which is emitted by this nanoparticle and then bringing it out and detecting it, okay? So by having this hyperbolic metamaterial, so we are modifying the so-called density of states. We are making the possibility of this photon to come out of the nanoparticle and into this hyperbolic metamaterial medium, and then this antenna on the top is going to help us in directing it in one particular direction, right? So we demonstrated such things, and also for single photon emission from these structures, right? So if you want to make a unit cell, if you're talking about a unit cell, which is an atom or an ion in a normal crystal, here we are talking about a unit cell which is some particular shape, right? So it can be arranged, this particular shape can be arranged either as in periodic or in aperiodic random structure or a quasi-periodic structure. So if you have a periodic structure, for example, grating, right? This is just a one-dimensional grating. So these are long lines of gold, which are on top of a substrate in glass, for example. So what we know is the diffraction patterns, 2d sine theta equal to m lambda, right? D is the separation between two lines, the period, right? So once that is fixed and the theta, the incident angle is fixed, right? Given the order of m equal to 0, 1, 2, 3, or plus or minus 1, plus or minus 2, and all that. Now, when the m is defined, so the lambda at which this diffraction can happen is also fixed, right? So this d, theta, and the lambda are interrelated. You change one of them, the other changes, right? So which means that you'll get narrow resonances in these structures. So which means if you use a short pulse, we showed that this short pulse, a Gaussian pulse, is going to get distorted in shape and time, right? So you cannot couple a light of very short laser pulse into a metamaterial which is periodic in nature generally, right? So we showed that we can have this quasi-periodic structure. So instead of having a square lattice of dots, you can have this quasi-periodic structure. This is a 5-fold rotation symmetry, these flower-like structures which you see here. So which complex Fourier transform, which means large number of momentum vector scattering directions are possible for a large, with no polarization dependence or incident angle dependence in these structures. We demonstrated such structures and showed second harmonic generation from these and other things, right? I'm going very slow, so I'll quickly cover a couple of all dielectric metamaterials. So this is, for example, if you take a quasi-periodic structure, you take a silicon surface and you make the top surface with these hole patterns. So these hole patterns are made to have conical shapes. So this has larger diameter at the top on the surface, and it has lower diameter at the bottom inside the substrate. So what this means is it's more air-like at the top, because there is more air, more material of the substrate is removed from the top. So you have more air-like on the surface. So your impedance matching is working out well. And there is a slow adiabatic increase in the refractive index towards the substrate, because the diameter is slowly reducing, because of which we can reduce the reflection from air to the substrate, because the semiconductors have very high refractive index of 3.5. Air has refractive index 1. So the contrast is very high, because of which most of these optoelectronic devices have reflection losses. So large amount of light is going to get reflected. But by patterning the top, we could show that we can actually enhance the absorption by up to 15% just by patterning the top surface, right? So this is another concept known as optical reflectionless potential. So we designed these potentials from basic physics ideas. Like, for example, if you have quantum mechanics, we study about Schrodinger equation. So in the Schrodinger equation, we can study different potentials. So we can design potentials or for the refractive index now. So you can have the refractive index varying in a fashion like this, for example, right? So if it goes up and down in a very smooth fashion, and this entire structure is of the order of, say, wavelength. So this entire thickness is going to be seen by the one single wavelength of light, right? So individual layers are not seen by the light because, as I said, there is no wavefront distortion from each of these layers, right? So then this entire medium is going to act like one single medium. So you can actually couple the entire wave into one single thing, and we can suppress the reflection. So the potentials in quantum mechanics are known as reflectionless potentials. We showed that in optical domain, and we showed less than 0.5% reflection covering, say, 500 nanometer to 2700 nanometer wavelength range. So now, because this is broad wavelength, we could couple a 5 femtosecond laser pulse into a glass substrate and enhance its supercontinuum generation. So you launch, say, 800 nanometer wavelength pulse, you get a supercontinuum which is covering from, say, here in this case, like 400 nanometer to 1000 nanometer wavelength range are generated. Okay. So this is, I can stop here for some questions, or just I'll introduce the concept and then I'll stop. I'll not show all the results. So this is known as a bound state in continuum. This is another very important concept nowadays, which is very popular. So the idea here is, when you take the quantum mechanics 101 course, like, so we study what is known as the potential well problem, right? So in semiconductors, we know this concept as the quantum wells. You take a high band gap material, right? And in between, you put a low band gap material. So the conduction band edges and valence band edges are, they form a potential well, right? So this potential well is the quantum mechanical problem. If the low band gap material is dimensions are close to the de Broglie wavelength or the free electron wavelength inside the medium, so then you start seeing these quantum confinement effects, and the energy levels are quantized. So this is energy level 1, energy level 2. But above this barrier, you'll see this continuum of energy levels, which are shown by these dashed lines, right? Blue dashed lines. Now, what happens if you do not have a very nice plain high band gap material layers? If you have a rough layer, so for example, it's possible you're growing layer by layer. So that you have one layer of high band gap material, you have low band gap material on the top, and then you have another high band gap material on the on top of the low band gap material. So this interface can be rough, like what is shown here, right? It can be rough, which leads to a confined layer within these bound states, right? Within these, a bound state within this continuum, which I have showed on top of within these continuum layers, we can have a bound state, because now the barrier potential is not completely flat, because the composition can be different, right? Or thickness could be slightly fluctuating, so because of which you can get this fluctuation, right? Because of which you'll have another bound state within this. So this is a bound state in continuum. So you can have these concepts carried to, for example, metamaterials, right? So we showed different properties of it, borrow ideas from semiconductors, and then showed that we can have polarization independent bound state in continuum in these structures. Okay. Just to summarize, so the metamaterials are subwavelength feature structure designed for very specific purposes with very specific properties, whatever we want. Right? We can have metal and dielectric combinations, or purely dielectric materials to make these structures. So I showed examples of a perfect absorber metamaterial, which can have applications in optical filters, stealth coatings, biomedical applications as sensor. Right. It also showed a broadband dispersionless metamaterial. For example, it can have applications in photovoltaics. Right. So metamaterials can be designed to mimic properties of atoms in bulk materials and trapping atoms as well as generating single photons. These are all possible in these structures. Right. I showed two examples of optical reflectionless potential and bond states in continuum in all dielectric metamaterials. You can just not just the properties designing these, you can also make these things and can get into really exotic new domains where new technologies are possible. Right? So these are the people who are involved in the work, students and collaborators. So all these in blue are currently in the group at TIFR. So others have moved on. So a large number of engineering students who work in my group for their project 6 months to 1 year, right? So Aman, Harsh, right? So Arvind, right? All these are like most of them are short-term students, Manav, right? So all these are short-term students who did projects in our group and moved on to do their PhDs in Europe and in US. So the blue ones here are all the theory collaborators. All the terahertz work was done with Professor Prabhu, right? And funding is from TIFR and DST. So thank you.
Yeah, thank you, sir. It's very nice to see you again in the same form. It's actually the students you can act. It's a very interesting talk and a very interesting field. The people, those who have interest in higher studies or research in their future, they can think of a internship which is being provided by TIFR. You can visit the labs. They are really
and also NPL.
International standards. Yes, yeah, also NPL. So the government funded internships, 1 or 2 months, you can definitely look for that. You will be exposed to the latest technologies, cutting edge technologies in the world, whatever. Now I'd like to take up some questions. It's from a really interesting talk. So I can see Dr. Manjula is asking, so I will unmute her and I don't know. Dr. Manjula, I can unmute. Oh, yeah. Yeah, you can unmute. I think, yeah.
Yeah. Good morning, sir. Am I audible?
Yes, ma'am.
Okay. Sir, for example, nowadays we are hearing about nanoscale devices or machines, and we are expecting these devices to have communication facilities. Okay, if that is the case, which one do you suggest the best metamaterials for the fabrication of such devices or components?
Right. So it's not, there is no best metamaterial, ma'am. So we need to design our own metamaterial which will work. For example, on-chip antenna and receiver. Right. Now this antenna and receiver can be designed by us. They can be simple bow tie structures, or they can be simple meander kind of structure. So depending on the size, shape, and the application where we want to use, right? So we can design and choose the metamaterials shape and sizes.
Okay, thank you. Sir, I have 2 more questions. Like you have already mentioned some of the applications here. I can see that in biomedical applications and all. So I'm just inquisitive to know if it is in biomedical application, will having the knowledge of a single molecule is really essential for us. How does that matter?
It matters because we don't have to give so much blood each time we go to a pathology lab.
Okay.
So that's a critical thing. Right. So that's, if the sensitivity is higher, it just that we'll be able to possibly detect even before the disease is shows up in a strong manner. Right.
Okay. So can I relate to this right now? So for example, if things were already working and means implementable, then would these sensor be able to detect the COVID viruses at that particular scale and intimate us? Or at least can we foresee such devices or application areas in future, near future?
Yes, ma'am, certainly. Certainly. Right.
Okay, okay. Thank you, sir. Thank you.
Any other questions, students?
I have one question, sir. For this metamaterial structures, we are using that E-beam lithography to fabricate the device, like some nanoscales. So, without E-beam lithography, whether is it possible to fabricate the device in any unconventional way or conventional?
Right. The simplest thing which I started with before our clean room was even built in TAFR was to use two laser beams, make them interfere. Right. So you'll have dark and bright fringes, so you can get a one-dimensional grating, right? Periodic structure. Now, if you do partial exposure and then rotate your sample, so you can get a two-dimensional pattern. There can be circles, there can be squares, depending on the exposures. You can actually manipulate these things. This doesn't require very high-end equipment, right? So there are also, for example, nano imprint lithography. You need a mask, and then you can do with UV exposure or local temperature curing, like you can stamp these to have large area writing. Even with electron beam lithography, one of the drawbacks is you get finer features, but writing over large area will take hours, 10 hours, 18 hours, something like that. So it's not possible. So you can use a simpler nano imprint lithography to make large area patterns. Now there are these laser scribes, right? So have this 2-photon polymerization based technique where you can get really sub-micron features by laser exposure, right? You can either move the stage or move the beam to write these patterns whichever you want from the software directly. No mask is needed for this. Yes, there are several techniques which doesn't require very high-end equipment, costly equipment, or clean room and other resources, which are possible.
Yes, sir. One more question. Whether this metal insulator metal, these structures can be used as a metamaterials, and also that can we include this fabricated structures in metamaterials?
Yes, absolutely. So, for example, in the biosensor which I showed, it's basically an asymmetric fabricator, right? You have a very thin metal of say 35 nanometer. Then we have a dielectric layer, and then we have a very thick metal layer. So it's an asymmetric fabricator.
Okay, I think it's answered. So now any other students who have any question?
Okay, I think we don't have any question now. So I request our HOD, Dr. Ramesh Vadi, to continue this session and conclude this session.
Hello. So thank you so much, sir. Professor Venugopal, sir, for the very insightful presentation on metamaterials applications. I'm very much sure our students got deeper insights on the research happening and this innovative topic. Sir, I request you allow some of our students, interested students, to have some internship with you during summer or sometime. So we'll get back to you. Some of the faculty members will keep in touch with you, sir. So we'll be happy to host you sometime physically in campus, sir. Whenever you are available, please let us know. As our Pro-Vice Chancellor, sir, has requested, we'll be very happy to host you physically and conduct some sessions and training for our students here, sir.
Thank you. I really look forward to.
Yes, sir. And I'm very happy. I'm happy to know that some of our faculty members are already working in collaborating with you. So, Dr. Rana, so definitely we'll continue working further and take
Yes.
best utilization of your knowledge and experience. Definitely, we're looking forward, sir.
Thank you. Thank you, Dr. Ramesh. Yes.
So I thank you, Professor Narendra sir, for your time. Thank you all the faculty members and the students for their participation. So any questions, so feel free to write to Dr. Rana and Dr. Manoj. So we'll definitely communicate those questions or queries, any of your interest to work with today's our speaker professor. So we'll be sharing forward things. So we'll keep in touch with you, sir. So thank you very much for the session. Once again, thank you, sir. So I thank all the members also. Thank you, sir. Have a nice day.
Okay, there's some question there.
Oh, okay.
Yes, I mean, random nanocomposites, yes, they can have their own properties. Yes, they can be used as metamaterials. We can study their, look at their applications as well. Yes. That I showed quasi-periodic, random also useful. Yes.
Sure, is it clear? Thank you, sir, for your time and support.
Bye. Bye.
Okay, thank you. So we'll end the session and